Okay, let's talk about our basic rules for taking derivatives. We're not going to prove any of these rules. The proofs are out there. Up until this point, to take a derivative, we've done the difference quotient. Limit as h approaches 0, f of x plus h minus f of x all over h. Now we're going to have these rules that we can use from now on, and we won't have to use the definition, at least not very often. First rule is the constant rule. I would definitely recommend pausing and writing all these down in your notes as we go through. And this says, if your function is a constant, then its derivative is 0. Remember, derivatives are rates of change. Change in y over change in x, slopes of tangent lines. Constants don't change. So the derivative of a constant is 0. So right here, we've got g of x is -3, then g prime of x is just 0. We could look at that. Here's g down here at -3. Any line tangent to that is just the line itself. The slope of that line is 0. Derivatives spit out slopes of tangent lines. Okay, moving up a level. If you have a function that's just x raised to some power, then the derivative with respect to x is that power times x to the power -1. So you bring down the power and then decrease the power by 1. So for example, if f of x is x to the 7th, then f prime of x would be 7 x to the 6th. The 7 comes down front and then goes down by 1. Okay, the derivative is a linear operator. So all three of these really could be squished together into one rule that says the derivative is linear, meaning you can distribute the derivative over addition or subtraction, and you can pull constants out. So all three of these go together. The derivative of a sum is the sum of the derivatives, derivative of a difference. Anything you do with plus, you can do with minus. And most importantly, you can pull constants out. If you have a constant times a function, that constant comes in front, and then you take the derivative of whatever's left over. So if g of x is 3x squared, then g prime of x would be 3 times 2. That 2 came down to ground level times x to the 1st. Another way we could think of this is this would be g prime is 3 times the derivative with respect to x of x squared. So that 3 just comes along for the ride because that's a constant. And then derivative of x squared, bring the 2 down. That 2 decreases by 1. Either way, we just get 6x. Okay, if we've got this guy here, f prime of x, all the constants, first rule, I can distribute. I'm not going to write all this out. I'm just going to say it aloud. I can distribute. I can do derivative one term at a time because I have pluses and minuses. Okay, I'll write it out. I'm never going to make you write all this out. I just want you to see it. Derivative with respect to x of 6x squared plus derivative with respect to x of 3. And then again, see, it's just like with all those limit laws where we wrote it out step by step. I'm going to write this out, but I'm never going to require you to write out all these steps. So I'm pulling these constants out. Here, this is just derivative of a constant. There's no x in this function right here. The derivative of a constant is just 0. This is a constant times something that has x in it. That's why I had to pull the constant out and then take the derivative of whatever's left over. The derivative of x cubed, now I'm doing the power rule, will be bring the 3 down and then decrease the 3 by 1. 6 times the derivative of x squared, bring the 2 down and decrease that 2 down to 1, and then plus 0. And now I can just clean this up. We get what? 6x squared minus 12x. For a good exercise, it might be fun for you to, on your own, use the difference quotient. Limit as h goes to 0 of f of x plus h minus f of x all over h. Find this guy's derivative and prove to yourself you get the same thing. Okay, let's do one more in this video. We're going to find the equation of the line tangent to that function at x equals 1. And I don't know what this graph looks like completely. I know he's a parabola and he points up. He may live up here. He may live down here. I don't know. I'm just going to draw like a rough sketch. Here's x equals 1. We're looking for the equation of this line right there. Well, the slope of that line is the derivative at that point. So let's find the derivative. The derivative with respect to x, and now I'm just going to use all those rules we just learned. That will be 2x, 2 times 1, and then that 2 drops down to a 1. Minus, the 4 just comes along for the ride. The derivative of x is just 1. Derivative of x is 1. I'm going to write that on the side. The derivative with respect to x of x is just 1. Because you get x to the first that we're taking the derivative of. 1 comes down front. And we get x. 1 minus 1 is 0. What's anything to the 0 power? It's not 0. It's just 1. So my derivative function is 2x minus 4. So my slope of my tangent line will be f prime evaluated at x equals 1. That'd be 2 minus 4. That's negative 2. Now I'm going to write this. It doesn't tell me what form. I'm going to write this equation in point slope form because that's the least amount of work. I know an x value and I know my slope. I just got to find my y value. A lot of mistakes happen here. This y value right there is the y value on the original, not the derivative. I already know f prime of 1. I just found it. That's the slope. That goes right there. I know this is 1. That's my x value right there. The y value is the original evaluated at 1, not the derivative. So what do we get? 1 minus 4 plus 6. I think that's 3. So that would be 7 minus 4, yeah. So then in point slope form, we would get y minus 3 equals negative 2, x minus 1. If I wanted slope intercept form, I could then clean that up a little bit. That's a good place to stop on that one.